For oh, great. So the second talk for the symposium is by Elena Massara from the University of Waterloo, and she'll be telling us about cosmology with galaxy surveys. Take it away.
Thank you. I hope you can hear me well. Good morning, everyone. I'm very happy to be here today to talk about my research on probing cosmology with galaxy surveys. Sorry. Okay. Yeah. I think it's frozen.
Okay. Try to see if you see the
Yeah. Sorry, I think my laptop is frozen.
Oh no. Okay. Oh, something. Okay, you did it.
All right. Okay. So in my talk, I will first introduce what are the big questions in cosmology. Then I will tell you why we can probe cosmology using galaxy surveys and show you some of the recent results. I will also speak about future galaxy surveys, and in particular, I will be telling about Euclid and the Roman Space Telescope. I will introduce novel statistics and methods that we can use to analyze these future datasets. And I will also talk about the role of machine learning in analyzing these datasets, but also understanding the systematics that comes with the new surveys. So I would like to start speaking about our understanding of the universe. And I know you just heard about this. So please bear with me. I would like to introduce some of the topics again to motivate better the second part of my talk. So, can you hear me? So for what we understand about our universe, at early time, we had a big expansion that we call inflation. And then the matter in the universe was very hot and dense. And as the universe cooled down, the light could decouple from matter, and we had a cosmic microwave background radiation that could be emitted from this plasma. The universe kept expanding and cooling down. We have the formation of the first stars and of the first galaxies. And today we see a universe that is still expanding, and its rate of expansion is accelerating. We have also an understanding of the energy content in the universe. We estimate that about 70% of the energy must be in a form that have negative pressure to explain the accelerated expansion of the universe. We call it dark energy, but we don't know what it is. And one of the main goals of future surveys and current surveys is try to understand the property of dark energy and its nature. About 5% of the energy is in baryons, and 26% is in another form of matter that we call dark matter because it doesn't emit or absorb light. And we don't know what the particles that form the dark matter are. And this is also one of the main challenges that we are facing nowadays in physics. And then a small fraction of the energy density in the universe is in neutrinos. And they also come with some unknowns. Neutrinos are elementary particles. They come with 3 flavors and 3 different mass eigenstates. Neutrino physics oscillation experiment determine the difference between the squared of pair of masses. And so they open up the possibility for 2 different scenarios. We have the normal hierarchy with 2 light neutrinos and a heavy one, or the inverted hierarchy with 1 light neutrino and 2 heavy ones. But with these experiments, we cannot measure the absolute mass scale of these three neutrino masses. However, this experiment could put a lower bound on the sum of the three neutrino masses that here I'm calling m nu. And so we have a bound equal to 0.06 eV in the normal scenario and of 0.1 eV in the inverted one. Recently also, Catherine put a bound on the mass of the electron neutrino to be 0.8 eV. But apart from laboratory experiments, also cosmology can set constraint on the neutrino mass because the universe is filled with neutrinos. And one of the tightest constraints that we have nowadays come from the Planck collaboration that set it to be, that set the sum of the neutrino masses to be smaller than 0.12 eV. So nowadays we have a standard model in cosmology that was able to explain the observation that we have in our universe, and it encodes all the information in few cosmological parameters. We have omega matter, the matter energy density of the universe, omega baryon, the amount of baryons, H telling us the expansion rate of the universe, and S describing the perturbation in the early universe and how they change with scales, and sigma 8 that tell us about the amplitude of the matter fluctuation today. And apart from this standard model, then we have many extensions, and an obvious one comes from particle physics experiment. We know neutrinos are massive, and so also the parameter m nu need to be introduced in our standard model to describe the neutrinos. And then we have other extensions, for example, describing different many different properties of dark energy and its equation of state. So in this talk, I would like to discuss how we can shed light in all this unknown about our universe using galaxy surveys. And in particular, I will be talking about two different probes, cosmic voids and Mars power spectra. I will define them later, but before I would like to discuss why we can actually use galaxy surveys to study cosmology. So here I'm showing a video about the evolution of the dark matter field in an embodied simulation. We start from very early time where the matter density field is almost homogeneous, and then we have that small overdensities start to attract mass towards them and building up structures, while the low density regions start to evacuate mass and becoming more and more empty and larger, until we arrive at the time today when we have a particular structure, the matter resembles a particular structure in our universe. And you can see it even better in this picture where we have a 2D projection of the matter density field. And you can see that it resembles a web where the nodes are very dense regions that we call halos. They are connected by filamentary structures, and between these structures, there are the emptiest regions in the universe that are the cosmic voids. But we don't observe the 3D distribution of the total matter field. We only observe the light coming from the galaxies that you see on the right panel. And luckily for us, the 3D distribution of the galaxies trace the underlying distribution of the dark matter field. So that using observation and studying the 3D distribution of the galaxy field, we can infer the full 3D distribution of the matter and study cosmology. So when we observe galaxies, we observe their direction in the sky that can be described by two angles. But if we want to have a fully 3D distribution of a 3D map of our galaxies, then we need to estimate their distance from us. And we do this using the following effect. So while the photon, the light coming from the galaxy, travels through space to reach us, its wavelength gets stretched and basically it goes towards the red part of the spectrum. And so we can define the redshift as the ratio between the observed wavelength and the emitted wavelength. And the redshift then is a proxy for distance, because the higher the redshift, the farther the galaxy is from us. And assuming a cosmological model, we can then produce a 3D map of the galaxy field. Now, it's very hard to infer cosmology from the full 3D distribution of the galaxies. That's why we compute summary statistics. And the most used statistic and the most that give them the most results is the two-point function that measure the pair of galaxies at a given distance and compare this number to a random distribution, so that we obtain the correlation function that you see on the top panel, and its Fourier transform is the power spectrum. Now you can see that in the correlation function, there is a particular feature, a peak that we call the baryon acoustic oscillation peak, and it is a remnant of physics happening at very early time, when the universe was hot and dense, and acoustic oscillation could propagate through this plasma, and they got frozen at a given scale when photons could decouple from the matter. And an imprint of these scales can be found today on the distribution of the galaxies, that here has been exaggerated in this picture on the left, but it's still present and visible in the correlation function through the BAO peak. And measuring the position of the BAO peak, it's one of the ways to infer cosmology using galaxy surveys. And in particular, we use two different probes. The first one is redshift space distortion. And it's due to the fact that when we measure the redshift of a galaxy, the redshift is not just due to the fact that the universe is expanding, but it also there is also another component coming from the fact that galaxies are moving. And if a galaxy moves away from us, then it appears as more distant. If a galaxy is moving towards us, then it appears as closer. So if we have two pairs of galaxies, for example, on top here that are infalling towards each other along the line of sight, they will appear closer. If we have two galaxies that are moving far from each other, they appear as farther, as at a larger distance. And this might seem systematic, but if we know how to model it, it contains a lot of information. In particular, it can tell us about the growth of structure and constrain the parameter f sigma 8 that depends on our cosmological parameter omega mater and sigma 8. Another probe is the Alko-Paczynski effect. It's due to the fact that when we map redshift into distances, we assume a cosmological model. If the assumed cosmological model is slightly different from the one of the universe, then a configuration of galaxies that's symmetric, as the one that you see here on top right, get distorted by assuming a wrong cosmology. And again, this might be a systematic, but if we know how to model it, it tells us about the angular and radial distance at the given redshift of the galaxies, and it allows us to study the expansion history of the universe. And galaxy surveys have been used to probe to study cosmology. In particular, here I'm showing results from the EBOS collaboration that measure both the growth of structure and the expansion history of the universe up to high redshifts. And from that measurements, they obtain some constraint on the cosmological parameters. So their constraints are here in blue, and the other colors show constraints from different probes, for example, weak lensing, cosmic microwave background, and supernovae. Now, what does the future hold us? There are a lot of new surveys that are going to come online, and in particular, here I would like to talk about Euclid and the Roman Space Telescope, because of two surveys that I'm directly involved with. Euclid is an ESA mission that's scheduled to launch in a few months. Its goal in understanding the origin of the cosmic acceleration. And the wide survey is going to observe 15,000 square degrees of the sky that correspond to more than a third of the sky. It will do both spectroscopy and imaging, and it's expected to observe about 30 million H-alpha emitters between redshift 0.9 and 1.8. The Roman Space Telescope is instead a NASA mission. It's going to be launched later on in 2027, probably. And its high latitude wide area survey will observe about 2,000 degrees, square degrees of the sky. It's about 5% of the sky. It will do imaging and spectroscopy, and it's expected to observe 10 million H-alpha emitters between redshift 1 and 2, and 20 million O3 emitters between redshift 2 and 3. And all these numbers have been obtained by assuming that we can identify two lines in each spectra, and we can use these two lines and their wavelength to estimate the redshift of the galaxy. But if we allow for a single line identification, we will have a much larger sample of galaxies in the survey, and I will go back to this point later on in my talk. So now we can compare Roman and Euclid. Roman is going to observe a smaller fraction of the sky, but it's going to observe much fainter objects than Euclid, and so it's going to observe a much larger high density of galaxies. On the other hand, Euclid will observe a much wider area, but it will observe a slightly lower density of galaxies. But both of them are going to be extraordinary in sampling the galaxy distribution up to high redshift, and with very incredible detail, allowing us to study the small scales of the clustering properties of our galaxy field. And the small scales contain a lot of information. Here, I'm showing you an example of what's the information content in the matter power spectrum at different scales. So this is a Fisher analysis that we did in n-body simulations. The red contours show the constraints on the cosmological parameters that we can obtain using the power spectrum on large scales. And the blue and the green contours show the same analysis, but when we include smaller and smaller scales. And you can see that when we include smaller scale, we shrink the contours, and then we can improve the constraint on the cosmological parameters. But while the galaxy field is almost Gaussian on very large scales, and so all the information is in the power spectrum, on small scales, the density field is non-Gaussian due to gravitational evolution, and therefore the power spectrum cannot completely describe the distribution of galaxies on these small scales. And that's why there is information beyond the power spectrum. And so there are different ways in which we can retrieve this information beyond the power spectrum. One is using higher order statistics, for example, 3-point function, 4-point functions. Another way is studying different summary statistics, for example, related to peaks, voids, or really many others. And a third way of doing this is by applying nonlinear transformation to the galaxy field in order to Gaussianize it, so that the 2-point function of this now Gaussianized field contain most of the information coming from the field itself. And in this talk, I'm going to talk about voids that belong to the second categories and Mars power spectra that belong to the third one. So let's start with cosmic voids. Cosmic voids are the very low density regions of the universe, and we can identify them and build many statistics with them. In particular, they are very interesting because they are very sensitive to the sum of the neutrino masses. And you can see this by looking at these two pictures. So on the left, there is the distribution of the cold dark matter in an embodied simulation. On the right, there's the distribution of the neutrino density field. So while the cold dark matter field exhibit structures on small scales, and the density field can reach very high values, about 200 times the mean density of dark matter, we have the neutrino density field doesn't exhibit structures on small scales, and also its density field, it's pretty homogeneous. The density is very close to the mean density of neutrinos. So neutrinos are basically a background, and being a background, they impact different regions of the large-scale structure in different ways. In halos, like the node of the cosmic web, there is a lot of dark matter. Neutrinos are a background, and because of that, they are a small fraction of the total matter in halos, and they don't change a lot the evolution of halos. But voids are by definition devoid of dark matter, and neutrinos are still a background. And because of this, neutrinos are a non-negligible fraction of the total matter in voids. And therefore, they are going to change and determine the evolution and the dynamic of the voids themselves. So we can now look at, for example, some statistics and try to understand how they change depending on the neutrino mass. Here I'm showing the void size function, that is the number density of voids as a function of their size. In red, I'm showing you this quantity in simulation where we have massless neutrinos. And the other lines show results in simulation where neutrinos have different value for their mass. And you can see that as we increase the number, the value for the neutrino mass, we decrease the number of large voids. And this is understood by the fact that neutrinos are a background component. They add mass to the void that now cannot expand as fast as it would do if neutrinos were massless. And so effectively, when we have massive neutrinos, voids are less evolved and smaller. We then try to understand what's the information content in voids. And here is a result from a Fisher analysis that we obtained in n-body simulation, and I'm showing you the constraint on the neutrino mass and sigma 8. So in red, there are the constraints coming from the power spectrum. In blue are the constraints coming from the halo mass function that count how many halos there are of a given mass, while in green are the constraints coming from the void size function, so how many voids as a function of their size. And you can see that all these constraints are have different orientations, and so combining all this probe, we can have much tighter constraints on both sigma 8 and the sum of the 3 neutrino masses than using one observable alone. And so voids seem to be really a complementary probe to clusters and power spectra analysis. Another very successful probe built using voids is the void galaxy correlation function that cross-correlate void centers that here I'm showing as stars with a full galaxy field. And this quantity basically describes how galaxies are distributing around void centers. So we can look at the monopole and quadrupole of this quantity. The monopole in blue is going to describe the isotropic part of the statistic. So we have the void galaxy pair on the y-axis and the distance to the void center on the x-axis. So if we are at a small distance from the void center, there are very few galaxies, therefore very small number of void galaxy pairs. But as soon as we go farther from the void center, this quantity increases. And in orange is the quadrupole of this statistic that measure instead the anisotropies arising from the distribution of the galaxies around the void centers. Now, both the monopole and quadrupole of the void galaxy correlation function are sensitive to redshift space distortions and Alko-Paczynski effects. So in the same way as we were probing the growth of structure and expansion history of the universe using the galaxy correlation function, we can do the same using the void galaxy correlation function. And I'm working with a student at the University of Waterloo in trying to finalize now this project where we try to understand how well we can constrain the growth of structure and expansion history of the universe using the void galaxy correlation function obtained from the luminous red galaxy sample in the SDSS survey. So here in gray is the contour coming from galaxy clustering, so the 2-point function of galaxies. In red are the constraints coming from the void galaxy correlation function. And you can see that the constraints are orthogonal to each other. So by combining them, we can again get tighter constraint on cosmology. And this complementary of voids to galaxy clustering bring me to the next topic, which is Mach power spectra. So when we have a galaxy distribution and we compute the 2-point function, we are measuring pairs of galaxies. And most of the galaxies are in very high density regions of the dark matter field, which means that the 2-point function is mostly sensitive to the high density regions. Now, is there a way in which we can build a 2-point function that is instead more sensitive to low density regions, for example, voids, that we see are complementary probe to the galaxy power spectrum? And a way to do this is by using marks, and in particular by weighting the galaxies by a mark that is a function of the environmental density around the galaxy itself. So that, for example, we can upweight galaxies that are in low density regions. And in the bottom panel here, I'm showing such kind of transformation where we are upweighting low density regions. And so if you compare these two plots, you can see that, for example, where there is a void on the top panel in blue, that region has been upweighted in the lower panel. And so if we measure the 2-point function of these two fields, we have that on top, we have the standard galaxy power spectrum, computing the two fields, the 2-point function on bottom, we obtain what we call the Mach power spectrum. Now, we can ask ourselves also, what's the information content in the Mach power spectra? And we performed the Fisher analysis on simulations using galaxy catalogs in order to understand how much information there is in this Mach power spectra. And we use the power spectrum as a benchmark to quantify how much more or less information there is in Mach power spectra. So here in orange, you can see the constraints coming from the standard galaxy power spectrum. And in green are the constraints coming from a Mach power spectrum that upweight low density regions. So you can see that the constraints improve, and in particular, they improve for sigma 8 and the sum of neutrino masses. Now, while for each galaxy distribution, we can compute only one power spectrum, we can compute multiple power spectra from the same galaxy distribution. And this is because we can, in principle, apply different transformation of the initial density field. And if we apply different transformation, all of those upweight low density regions, we can obtain different Mach power spectra and use all of them as our probe to probe cosmology. So here I'm showing you the results on constraining cosmology, where we use 4 different Mach power spectra computed on the same galaxy field. And of course, all these Mach power spectra are correlated. And at some point, we saturate the information coming from them. But different ones sample the distribution in different ways and highlight information from different parts of the galaxy field. Yeah.
Is it 4 Mach? You mean 4 times using the same Mach but weighted differently?
Exactly.
Mach to the second power, the third power, that's what.
Exactly. It's a different mark because there is not only the power, but there is also how we define the local density. Is it defined on small scale or on larger scale? So there are a lot of parameters entering, and all of them define the mark. And so we can see here that we have great improvements using mark power spectra compared to using the standard galaxy power spectrum alone. And in particular, we have improvement of about 2 or 3 times for all cosmological parameters and of 6 times for sigma 8. Yes.
Maybe you can explain in the end. You perform a known distortion of the data with your marking, and yet that gives you more information.
So, yeah, so this is a nonlinear transformation. Basically, we are taking the initial galaxy field and multiply it by a mark. But this mark depends on the galaxy field itself, the initial one. And so basically, when we take the 2-point function of this marked field, this 2-point function contains higher order statistics of the initial galaxy field. So there is information also because we basically have 2-point function, but also 3, 4-point function, and so on. Okay, so if we want to go from a Fisher forecast to really using mark power spectra to analyze the real data, we need a model for mark power spectra. So we developed a perturbation theory model to describe them. And as you can see, here we have the real space and redshift space counterpart of the mark power spectra. They can be described pretty well by this perturbation theory model, but as all perturbation theory model, they cannot really be pushed to very small scales, so to high K. On small scales, they are going to be inaccurate. And so the other way to use the statistics and push them to small scales where we know there is a lot of information is by using simulation-based models. So they are models where we run an embodied simulation, find halos, populate them with galaxies, eventually introduce all the systematics that we have in our survey and the survey geometry, and then we can compute the statistic directly from this pipeline, be it the power spectrum, the mark power spectrum, any statistic. And the good thing about simulation-based model is that we can also then do simulation-based inference. So we can rerun the same pipeline many times, changing the cosmology and the galaxy bias to describe our data, and train a machine learning algorithm to learn the posterior distribution of cosmological parameters. So such a framework exists. It's called SimBig. Chang described it in very detail, this framework before. We had the first 2 papers that came out last year where we described the model, and also we tested it using the power spectrum. And we saw that using basically using the power spectrum, being able to use the power spectrum down to small scales, we can improve the cosmological constraint, especially on sigma 8, compared to other analyses where they use analytical model and they cannot really push the analysis down to small scales. So as part of this collaboration, my main role is introducing the mark power spectra analysis into the pipeline and do the first mark power spectrum analysis with the CMAS data from the SDSS survey. And I'm also co-leading the effort of introducing the void analysis in the same pipeline and do the analysis on the CMAS data. Now, looking at the future, these models are very promising, and we will need to adapt them to different surveys, for example, Euclid and the Roman Space Telescope. And in order to do that, we need to, for example, account for different volumes, different number density of galaxies. And these are all challenges that we are going to face going ahead. But another challenge when analyzing future data sets coming from Euclid and Roman, especially, are interloopers. Interloopers are galaxies that are for which we mislead a line in the spectrum, so they are placed at the wrong distance from us. And in particular, if we are going to allow for a single line identification with Raman, because maybe we want a very dense sample at high redshift, there at high redshift, the main line, the main target line is the O3 line. But we can have the possibility that there are galaxies with a faint O3 line, but a very bright H beta line. The H beta line is close by. It cannot be distinguished by photometric measurements. The H beta and O3 line cannot be distinguished by photometric measurements. So if we have this kind of spectra, we are going to assume the line we are seeing is an O3 line. We are going to assume the wrong emitted wavelength, and so determine the wrong redshift and the wrong distance of the galaxy. And all these type of galaxies are going to be placed at about 95 megaparsec closer to us. So this introduces a big systematic in our mapping of the galaxy distribution and on all the statistics that we are going to build on top of them. And in particular, it's going to introduce an asymmetry in the two-point correlation function of galaxies. Here I'm showing the correlation function for different fraction of interloopers, Fi, in our catalog. The blue line is when we have 0 interloopers. And then the other colored line are when we increase the number of interloopers. And increasing the number of interloopers, you can see that the amplitude of the correlation function change in different ways on different scales. And in particular, the position of the BAO peak gets shifted towards smaller scales. And as I said before, the position of the BAO peak is used as a cosmological probe. So this is going to be problematic for the BAO analysis with Raman. And so when we do the BAO fit, usually we describe the position of the BAO using the dilation parameters. They are called alpha and epsilon. Here I'm showing the results from the standard BAO analysis when we have interloopers in our catalog and we don't take into account that they are there. So in the y-axis, there are our estimation for these parameters minus the true. So we want the data, the points to be in the line y equals 0 in the black line, on top of the black line. So you can see that when there are increasing the percentage of interlooper in our catalog, we have more and more deviation from the expected value of these dilation parameters, and we have a larger bias. Now, I've been working with a student at the University of Waterloo in trying to include the effect of BAO in the fitting, and we were able to obtain a model that is able to take into account their effect and give us unbiased estimation of the position of the BAO peak, even for very large fraction of interloopers. And this model is very nice because it gives for free the estimation also of how many interloopers we have in the catalog. Here are our results. And as you can see, we have a good prediction for small fraction of interloopers, but when in the catalog there are larger fraction of interloopers, then our estimation is again biased. So is there another way in which we can resolve this interlooper problem, and especially at the density field level, so that we can mitigate it for all the observable and all the statistics that we are going to measure out of the Raman galaxy catalog? A way to do this is using graph neural networks. Graph neural networks are a way to describe the 3D distribution of the galaxy field using graphs, where we have that the nodes of the graph are the galaxies, and the distribution of the galaxies, the relative distance, is described by edges. And we can input some attributes on the edges and on the nodes. In our case, we added information about the relative distance of the galaxies in the edges. And once we have this graph, we can then train a neural network to learn the different patterns introduced by the interloopers in our galaxy catalog, and train it to predict the fraction of interloopers in the catalog. Here I have a preliminary result of a model that we train in this way. In the x-axis, you can see the true fraction of interloopers in the catalog, and on the y-axis, there is the prediction. So we want our points, our predictions, to be on the line y equals z, which is the black line. And as you can see, we have that the points are on top of the black line. There is a spread around it, but there is no bias, and we can get an estimation of the fraction of interloopers with an accuracy of about 2% and a precision of about 0.25. So I hope I convinced you that we have a bright future ahead with a lot of data coming, especially from the Roman and the Euclid missions. They are going to sample the galaxy field up to very high redshift with unprecedented details. And this allows us to probe the small scales of the galaxy clustering. A way to do this is using void science, which is very promising in constraining the sum of neutrino masses and do, in general, the cosmological analysis. Here, I'm showing preliminary results on a forecast on how well Euclid will be able to predict, to measure the growth of structure and expansion history of the universe using the void galaxy correlation function. Which are the purple line here. And so we predict that we can achieve a 0.3% precision in the expansion history and 3 to 5% precision in determining F sigma 8, the growth of structure. Also, Mar-power spectra that take information from low density regions through nonlinear transformations seem to be very promising in constraining cosmology. And here I'm showing some very hand-wavy predictions for constraints coming that we can obtain using Mar-power spectra with Euclid and Roman. These predictions have been obtained by rescaling the Fisher results that we had in simulations to the volume of Euclid and Roman. So they don't take into account that the galaxies of this surveys are at a different redshift than the one in our simulation. We have also a different population of galaxies in our simulation than one we would observe with Euclid and Roman. But we are expecting precision constraint on both sigma 8 omega matter and to be able to detect the minimum sum of the neutrino masses with 1 to 3 at the 1 to 3 sigma level. Also, machine learning techniques are going to be very promising in helping us analyzing this new data, accessing small scales, and also taking care of the systematics coming from these new data sets. I've shown you that they can predict the fraction of interloopers, but I think we can be even more ambitious. We can try to have them reconstruct the BAO position without interloopers. And we can also use them to classify galaxies to understand which are likely to be interloopers so that we can directly take them out of our catalog and then being able to perform the analysis with all statistics that we want to use. And so we have a lot of data, a lot of new information coming out. I'm very excited to see where this goes. Thank you.
Yeah. Thank you, Elena. Question. Oh.
So what is the final results for the limit on the neutrino mass coming from the analysis of voids?
So I showed before these constraints. The constraints are very small, but these have been obtained assuming that we can see the 3D distribution, we can observe the 3D distribution of the matter field, which is not possible. So we haven't done the forecast using galaxies yet. So these are constraints are very tight. We are able to constrain it at a few sigma level. So being able to constrain the minimum sum of the neutrino masses at few sigma level, but this won't probably be possible with voids and galaxy power spectra when using the galaxy field, when having only information about the galaxy distribution. And then, we find voids in this galaxy distribution. So I don't have the number for the very, the observation, what is possible to observe, but we are working on this.
Yes, because at the very beginning, you showed some limits from Planck and from Catherine.
Yes.
Rather than Catherine, that suffers from final state interactions and so on, perhaps you should also quote the value coming from the non-observation of neutrinoless double beta decay, which gives a limit. In fact, there is a tremendous amount of activity in the nuclear particle physics community trying to determine the mass of the neutrino from the observation of the double beta decay, neutrinoless.
Thank you. I will give a look to that. Thank you.
Okay, thank you for the plug.
Elena, a lot of great stuff. A quick question about the interlopers. You said one way to go after and determine the fraction of interlopers would be to go to the neural graph networks, machine learning techniques. Can't you do something much simpler? You have two samples of galaxies. You have the ones for which you have, two emission lines, and you can compute a correlation function for them. You have the one for which you have one emission line. You can compute the cross correlation between the two emission line and the one emission line galaxy. Sure. Compare that to the outer correlation function of the one with two emission lines, and that ratio is a direct measure of the interloper fraction. So isn't that the much more straightforward empirical way to go after the interloper fraction?
So, but this assumes the fact that we know the galaxy bias, or that is the same galaxy bias.
Right.
In
the assumption is that both follow the same density field.
And so basically, it's not guaranteed that that's the case.
But how does your neural network, graph network, know about this without feeding it simulations, and the simulations are not reality?
Right. And so basically we train it with the very different cosmological models and galaxy bias scheme, so that for what we see, we are able to marginalize over cosmology and galaxy bias, and really determining what are the anisotropies introduced by these interloopers. So basically the way around is basically training on different galaxy bias.
Thank you. Interesting. Very interesting. I have a bunch of questions, but I'll just ask one. You compared Roman and Euclid, and they'll be surveying different areas to different depths, so different volumes, I guess. So you'll be seeing slightly different populations. But what is the driving quantity in determining the power to constrain cosmological parameters? Is it the total number of galaxies? Is it something else? How does it, who's going to do better and why? Yeah.
So usually the larger the volume, the more information we can get, but also we need to have a high density of galaxies in order to access these small scales that we're talking about, because we need to be able to see the details of the distribution of the 3D galaxy field. And so it's really like both these things that are important. And so on one hand, Euclid is going on to observe larger volumes, and Roman instead the higher number density of galaxies. And what I didn't mention is that while Euclid, the strategy of Euclid is set, because it's going to launch in a few months. The strategy of Roman, it's not set yet, and it's going to be informed by what Euclid is going to find. So it can be that what I show will change a little bit, like the strategy will change. It all depends on what Euclid will observe. And so we will understand how to better tailor Roman.
Okay, any other questions?
I'll ask one more question. You sort of alluded to it, and the entire talk didn't see the word of bias come into play. And now, of course, you and I, we all know that this is very important. So can you say a few words? I mean, the real hard thing to deal with, and especially when you go and include small scale structures, is the assembly bias issue. The fact that, you know, the bias, the first order, we think is a mass dependent term. We can figure that out, but then there's all the other stuff. And what strategy do you have in mind to sort of, you know, marginalize over the uncertainties there? Because I have run out of ideas, and I have given up the hope that we can get to 1% precision. I'm a very pessimistic old guy, but enlighten me.
So even with
That'd be pessimistic. How can we marginalize over all the assembly bias issues and get to the % level accuracy?
So you don't think we can do this using, for example, hydrodynamical simulations? Are we talking only? So I think that we can explore different venues, and yeah, in particular about, I would say that the good thing about these machine learning algorithms is that we can try to marginalize over these effects. And so if we have many different models being basically describing the galaxy bias, we can aim to be able to describe, to contain also what our universe is, and train this model to marginalize over it. Then if we are instead interested more in the astrophysics questions, really about galaxy bias, then I'm not sure how to handle this. But if we are strictly interested in cosmology, maybe, yeah, this machine learning algorithm can help us in this way. That's the hope, but it's still to be determined.
All right, well, let's thank the speaker again.